Okay, when I was teaching the emulsion part, so there we said phase inversion, right? So phase like water cut, you take certain amount of oil, you add water, and create emulsion. So when there is no water, is 0% water cut, and water increasing. If completely it becomes water, there's no oil is there, so that will be 100% water cut. Okay, so when certain amount of oil is there, you're adding water, viscosity will increase. After 60-70% around, viscosity will be maximum. Okay, after that suddenly viscosity drop will be there. So what is happening? Water, small amount of water in oil. So this side is water in oil emulsion. Okay, now small amount of water, big amount of oil. So this is water in oil emulsion. But after phase inversion, so suddenly this drop is happening. So this is oil, this zone is oil in water emulsion. So the water amount increase, so oil becomes small particle, water become continuous phase actually. Okay, so this become oil in water phase. When water amount was lower, so the time oil continuous, water particle or droplets were there inside oil. Okay, so the phase change occurring, this is called phase inversion occurring nearby 60-70% of water cut. Okay, so one of my PhD student Bellery, he did this sort of experiment. Initially he mixed this fluid with different water cut, and he made add some chemicals so that emulsion can be stabilized. After that he did some experiment. What will be the effect of emulsion on centrifugal pump? Okay, so this figure you see, okay, this top right corner figure. Okay, here you can see around like 60% nearby phase inversion happening. Phase. Okay, in phase inversion, what is happening? Suddenly viscosity is increasing very high. Okay, then viscosity dropping, right? When viscosity increasing, actually your head or pump performance will be dropping. So what is happening in the head development? Head development means fluid is flowing through the impeller channel, right? Fluid, water or oil is flowing through the channel. Now viscosity increase, viscosity resistance to flow. So fluid will not try to flow because of this viscosity. This one particle will be pulling another particle, pulling back, and it will be sticking on the surface, so it will be pulling back. All the particles pulling back each other. So fluid will not move to the exit. It will move, but the speed will be lower. So that means total velocity will be lower. So velocity converted to head will be lower. So whenever viscosity very high, your pump head became lower. Okay, you see this area. Okay, pump head become lower, efficiency lower, flow rate also got down. Okay, because of viscosity. And for different water cut, he again try to play things. Very high water cut, you see this one, this curve. Very high water cut, you got higher head. This is head in meter he has taken. If you can make in feet, then multiply by approximately 3 times. Okay, meter to feet, if you convert, approximately 3 times, you just multiply. So it's like if you're showing 6 meters, 6 meters means 6 into 3, 18 feet or 19 feet about. This was single phase impeller. This one, the same impeller was tested actually, not this one. This was cut. So other one, this one. Okay, so this impeller was tested, actual impeller actually. This is not metal made, this is softer material made actually. You can see this one, very soft material. So this was tested by Bellery during his PhD work. Okay, so he got, during phase inversion, head or pressure dropping. Okay, when pressure dropping, you got different curves. You got the right side curve, and for head dropping curve for different water cut he tested. for very high water cut, he got very high head, and this one is here. Okay, so when water percentage very high head, oil percentage also very high, higher head. But if you are mixing in between 100% water or 0% water, your head is lower. So if you have emulsion in wellbore, actually your head is going down. Okay, head is going down means if there is any water injection changing, water coming to the wellbore because of drive mechanism, then your emulsion property will change. If you have some emulsifying agent also, so in that case viscosity will change because of emulsion change, phase inversion will occur, in pump performance will change. So initially you buy a pump and you see pump is working nice for certain emulsion, okay, but after a certain time you see the pump performance changed, and if you do not know this physics, then you will be clueless what is happening there. Okay, you are trying to develop 10,000 feet depth, 10,000 feet water liquid column, but finally it is developing maybe 9,000 feet. Okay, so what is happening? Because of this phase inversion or water cut change. Next is multi-phase effect. Okay, this picture shows, left picture shows, this is a multi-phase centrifugal impeller and diffuser or multi-stage ESP. Okay, and this is also work done by one of my students in masters MS course, Rahit Adav, and he published one journal paper. So it is like, this is impeller, okay, this is diffuser, so this is impeller I. Okay, so fluid is entering here, then exiting here, impeller entering here, this side, entering here, exiting here, then flow turning will be happening because of casing, and this is impeller, this is diffuser, this is mixed flow. Actually, why mixed flow? You can see almost 45-degree angle. Impeller is making almost 45 degrees, so it's a mixed flow impeller. Okay, so mixed flow. Now this is diffuser, diffuser entering here, diffuser entry of fluid, and diffuser exit of fluid. Okay, diffuser exit fluid, again impeller entry, in diffuser, this is entry diffuser, diffuser entry, impeller, impeller exit, this is I, so impeller entry. Okay, so from I, fluid will be entering, exiting, diffuser entry, diffuser exit. So this will be continuing, 1 stage, 2 stage, 3 stage, diffuser exit, impeller entry, diffuser impeller exit, diffuser entry, diffuser exit. So this whole sequence will go on one by one. So this is one stage. Okay, stage 1, this is stage 2, this is stage 3, this is stage 4. So this way impeller will be stacked, the stages will be stacked one by one. And right side picture, it is again from the same paper. You see this impeller, you see impeller A. Okay, impeller is like this. Okay, white portion is impeller. Okay, so impeller at entry, this is I. Okay, impeller entry is happening here, impeller exit. Okay, impeller entry is happening here, impeller exiting here, fluid entry, diffuser, this is diffuser is here written there, this is impeller, the diffuser entry here. Okay, diffuser exit here, this is diffuser. Okay, diffuser exit here. So fluid is entering and going through this like this. Again, it will be going like this. It will be going. So you can match from left side figure to right side figure. Okay, and you can see the pressure. This is actually pressure picture. how pressure is increasing. So at inlet pressure is low, then when it is going to impeller exit, pressure increasing, and diffuser completely black here, you can see. So that means pressure developed already. There is no velocity very low and pressure head is increased. But inside impeller, velocity head is higher than pressure head. So that's why this picture is showing like this. And it is showing one direction. It will be three-dimensionally, will be rotating like this. Okay. And multiphase performance. Okay, again the Rohit Hatto papers I have taken, and he tested computational fluid using computational fluid dynamics with different gas volume fraction. So he has taken maximum 10% gas volume. So in centrifugal pump also 10-15% gas volume you can consider, but if you have more gas volume, the pump will have difficulty of pumping. So he took 10% gas volume, and doing CFD simulation, computational fluid dynamics, or experimentation in multiphase is very difficult, because the particle distribution and particle size, those things are very important during simulation. So whenever people will be doing CFD simulation or experimentation, they will be taking approximate size, approximate distribution. So that may not be true. Again, inside impeller, when fluid is flowing, the very complex flow situation will occur. So the particle will be breaking also sometime, particle will be joining also sometime, and lots of phenomena will be happening inside the impeller. That's why it is a not so simple task to simulate any multiphase flow through turbo machinery or pumping systems. So here you can see this flow rate and power here is calculated, and 0% gas volume we have. So this is 0% line, and 10% gas volume is here. Okay, in between several lines are there, because heavy research he has done some more designs and optimization. So you can see increasing, okay, 0% gas volume, increasing gas volume, your power input reduced actually in this case. Okay, and here right side picture you can see this impeller. This is suction side, this is pressure side. Okay, so what is happening if I take this impeller? Okay, impeller is like this. So impeller, this is suction side, this is pressure side, this is suction side. So one impeller is like this, another impeller will be here. Okay, another impeller will be here. So one circle. So in three dimensional we are not drawing, only we are drawing two dimensions, and white portion is actually impeller. Metal part is showing white, the fluid is not flowing through this one, but this channel is showing like this. This is the channel, flow channel. Okay, fluid is flowing through this. Now when it is flowing, pressure surface, it will have pressure surface, the fluid particle will be, the gas and liquid particle will try to separate from each other, because gas density, fluid liquid density different. So gas will be moving, gas particle, because of drag action, fluid will be dragging it, and because of gas lightweight, so gas will try to get some easier space. Okay, so somewhere gas will be getting segregated, somewhere gas will not get segregated, because of this fluid drag action and density difference action. Okay, so this was reported in this paper. Now pump intake. In centrifugal pump or ESP system, you have casing, okay, then you have tubing, and you have pump. Okay, so first there will be motor. Okay, motor, then there will be protector, then there will be pump intake, then there will be pump. Okay, the sequence if you see, first normally motor will be the bottom, then there will be protector section, and there will be pump intake, then pump. Then one more shaft will be moving from motor to the pump, and shaft, it will not be a single shaft, rather it will be connected, several shafts will be there, it will be connected properly. So torque will get transferred, not axial force, nor radial force, nor vibration. Okay, now up to 10% gas volume you are handling. Now when you are having gas in the wellbore, if you don't have gas, then you can use integral intake, or without gas assembly system should be there. But if you have gas, then you should use gas separator at pump intake. Okay, so this whole system actually, it will be including your gas separator, it will be having NPSH enhancer or called NPSH or inducer. Okay, and coupling is here. Okay, coupling is I'll show here. So in my pump there is one hole actually. Okay, this shaft is having one hole, so I have another shaft. This hole is like this. If you see from side, the picture is like this, then okay, it is like this. Okay, so another shaft end will be like this. Shaft end will have okay, so this cavity, another shaft outside will be like thread, not thread, like gear teeth sort of thing. So just you put here. Okay, so it will give enough axial alignment space and some radial flexibility also. Okay, so this sort of connection will be there. So this is coupling. So there will be spline coupling, flexible coupling, different types of couplings will be there. Now this shaft is going like this. Okay, through this intake section. So intake section can be rotary or static. Okay, static or reverse flow type. Reverse flow type means like pour boy gas separator you have seen. So well, fluid is coming here. Okay, so fluid will go through this one, and gas is going up. So gas bubbles. Okay, gas is going up and liquid is here. So where is that? Okay, so gas is going outside, but liquid going inside through somewhere, and liquid is going to pump. Okay, so liquid, when it is exiting, the pump intake section exiting, it will be entering directly to pump actually. Pump where? Pump I, impeller I, it will get that part. Okay. So this is reversible flow. Reversible flow means it's static, there is no rotation. Shaft is going through this one, but shaft is not giving rotation or torque to anything. And gas, because of its own density, it will move and it will flow through annular pipe. And liquid, because of high density, it will move down and will enter into certain path, and this path will lead directly to your impeller inlet or I section. Okay, so this is called reverse flow. Reverse flow gas separator. Okay, now next is rotary gas separator. Rotary gas separator, what is happening? You see this upper part. Okay, this rotary gas separator picture, upper part, this is shaft. Shaft, I said, it is cylindrical element like this, and it can transfer torque, basically torque. For ESP, it is transferring only torque. Okay, the shaft, one end you can see spline type. Okay, one end is like this. Okay, it is like this. Okay, and I have another end of the shaft just opposite. Okay, so just you can put another one into another end, so it will be easy to connect. So it is rotating, it will be smoothly rotating, and it will give enough axial misalignment. Okay, and shaft, how is it getting power or force from where? So it is connected to your protector, because protector shaft, through protector also a shaft coming, right? Motor, protector, then gas separator. So through protector the shaft is coming and it is connected to your gas separator or intake section shaft. So intake section shaft will have one inducer. Okay, what is the purpose of inducer? Purpose of inducer is to give NPSH, net positive suction head. Sometimes actual centrifugal pump will be requiring very high amount of NPSH, like 75 psi or something. So, but your wellbore condition may not be supporting that much. So what will you do? You will use one axial pump, axial pump. Okay, inducer, actually one axial pump. It will give certain amount of pressure and very high flow rate, certain amount of pressure, and it will be assisting main pump. So it is not giving actual head to anyone. It is giving, it is helper only. It is helping to main pump. Okay, and fluid is entering here through screen. From screen it is going out. It is going through your inducer. Inducer normally it will have 5 blades about, and from and multiphase flow. Okay, so gas separator is required when you have lots of free gas or gas is coming out from your mixture of fluid. Okay, so gas bubbles plus liquid, it will be flowing through this. Then there will be separation. This section will be giving lots of centrifugal action. Because of centrifugal action, that gas particle light density will not get chance to go outer wall. This is wall, right? This area wall. So what will happen? Liquid will not give any space to the gas. So liquid will take all this space. Okay, this outer wall space, and liquid will enter through this. It will go to pump intake or eye of impeller. And gas, because it did not get a chance to touch the outer wall, so what will do? Frustratingly, he will be touching this shaft area near. The radius will be very low and will be rotating like this. But high density fluid, liquid, it will be rotating with high radius. High radius means it will be touching the wall, and low density fluid, it will be rotating nearby shaft only. Okay, nearby shaft, you make certain arrangement, you collect the fluid and you pass through your gas discharge area, maybe tubing and casing independent annular area, you push there. Okay, so this is one gas separator. You create centrifugal action, high density fluid, high density liquid will touch wall, it will move and it will enter your pump intake section. While gas, low density, it will not get chance to get higher radius because liquid already taken that bigger space. Smaller, low power area, that nearby shaft, there they will be getting accumulated and it will be passing through one channel and it will go out to the system. Okay, this way, in this way you are separating gas. This is called vortex type separator, gas separator. Okay, I have taken from this picture from slb.com, Slumberger. You can see this is, they are saying it's a vortex gas separator. Okay, you are creating lots of vortex and you're giving lots of centrifugal action, centrifugal force. Same shaft coming from motor, that shaft is giving this inducer to create certain amount of pressure. Then you give some more rotation, separate gas. So gas is going out of the system and liquid you're entering into your impeller eye, impeller, diffuser, impeller, diffuser, impeller, diffuser, going out of the wellbore. Inducer. So I already talked about inducer. So inducer main purpose is not to give major head to supply water or oil to the surface. It will be helping. It is a helper. Okay, I can name it as helper. Helper. How it is helping? It is giving NPSH. It is increasing NPSH. Okay, it is increasing NPSH of the main pump, main centrifugal pump, radial flow or axial flow. Those pump will be requiring lots of pressure, inlet pressure. If you are not giving, cavitation can occur, vibration occur, pump can fail. So you need sufficient amount of NPSH. Then an inducer will come and say, hey, I can help you. You give me some rotation. The motor will give some rotation and it will be axial flow pump. It will give lots of rotation, lots of fluid will be flowing to the main pump. Okay, and head will be lower because axial flow. You can remember that radial flow will be head higher, axial flow head lower. Low specific speed centrifugal pump, this is, but axial flow, high specific speed, high flow rate, low head pump. Okay. Now flow separation problem, suction side during low flow operation is low, then vane or pressure side. Okay, no help to add head rather helps in NPSH. Okay, so it does not help to add head on the main pump. Okay, it is not designed for that purpose. It is just help for the main pump. Main pump is the main person. Okay, pump temperature rise. When fluid is flowing through the pump, so there will be lots of energy losses. And if you have very good amount of energy losses, then what will happen? The pump temperature will be going up, and whatever fluid is flowing, if fluid flow is very high, then the temperature will be taken away. The heat will be taken away by the fluid, and the amount of heat will be taken away based on your fluid flow rate and based on your heat capacity. Water is having the highest capacity, so if you are pumping only water, then life is beautiful. Water can take lots of heat. But if you are pumping only oil, so oil is capacity low, so your heat generation maybe will be significant. That may lead to some material and other issues. Okay, let's see the formulation. Hydraulic efficiency, P hydro. Okay, 7.368 10 power minus 6, 7.368 into 10 power minus 6 H Q gamma. H means head, Q means flow rate, gamma means gravity. Okay, water or liquid. And BHP, brake horsepower, P hydro by eta P, pump efficiency, and flow rate, (42.41) P hydro into 1 by eta P minus 1, and temperature 3501440 C Q gamma del TF. So therefore del TF equals H1 minus eta P 778 C eta P. So this formula will be used to solve this sort of problem, heat generation. So determine temperature rise of fluid, del TF. Determine temperature rise of fluid to the pump, where water specific heat is given, oil specific heat is given, and pump develops 7,000 feet head. Pump is 64%. Okay, so you have to use the formula del TW equals H1 minus eta P divided by 778 C eta P. So it will be 7,000, 1 minus 0.64, 778 into C value 1, eta P 0.64. So total coming 5 degree temperature will be rise. 5 degree Fahrenheit temperature rise will be there. For oil, H again 1 minus eta P 778 C eta P. So this will be giving 10 degree rise. Okay, because of heat capacity, your temperature rise will be more. Del T oil actually instead of water. Okay, if you are having water, heat capacity more, so temperature rise will be lower. Thank you very much.